Right. So before we really get into talking about attention mechanisms, I think it is good to motivate why attention mechanisms are needed. We are going to do that again as we go through the course itself, or through this chapter. But why transformers? What happened? Why did we even need transformers? So previously we used to have other architectures. Before transformers, we had what are called recurrent neural networks, RNNs. Those were very popular when it came to machine translation. Machine translation. But there are challenges, and we are going to briefly discuss some of the challenges that they had in this video so that we motivate why we move to transformers and why we move to attention and all of that. So, why do we, um, let's look at when we don't have attention. When we don't have attention. When we don't have attention mechanisms and we're trying to translate, for example, if we want to develop a language translation model, translating from one text to another, thing is we cannot just do it word by word, one word at a time, because languages, they have different grammatical structures. So for example, if we have German like this, and I'm just going to write it, I can't really pronounce it, and again, I'm I'm afraid that maybe I'll offend people when I pronounce it wrong. But so like this, and then yeah, okay, E. This is supposed to be ETZEN, right? We want to translate this German into English. If we're doing it one word at a time, this would be the result. I think if you can speak German, you can already see what direct translating this one word at a time would mean. So this would be the English, and then this would be you, me, help, this sentence to translate translate. This results in broken English, and because I did a bit of Mandarin. And Mandarin actually, when I think of Mandarin, I actually break English. I think in broken English, and that is grammatically correct in Mandarin, which is uh, which is weird because when you break English, maybe it's a weird way of learning, but then it's an understanding that the the languages have different grammatical structures. Just like you can see here, German and English, they have different grammatical structures. So doing it word by word, translating word by word, is it is not the best way to do it. It is wrong. So the correct would be, we would need some words would need to the correct would be, um to move some words or to give some words some information, because because certain words in the generation require access to words that appear earlier or later in the original sequence. Our original sequence here, so we would want this original sequence to be processed in such a way that when we are translating the words that need earlier words, it gets them. Words that are coming later also get them. So when you correctly translate, this can will stay can, this you will stay you. But then this help here, this help is needed now. This me is not needed. So this would need to come here so that it is a help. And then me would then come here. And this translate is needed now. It's not needed later. So would need a way for the model to pick this word in German and translate it immediately now into translate, and then this will come here. Can you help me? Okay, yeah, I forgot that there's a two. Can you help me to? And then that's when the translate will come in now. Yeah, translate. And no, I put this there. I put this. Can you help me translate this? That's when this will come now, and then sentence will come. Sentence. So you can see that there is a need for there to be something in the model that understands the whole sentence and then sort of arranges the sentence better when we are translating, not to just do it word by word. So deep neural networks were developed that have an encoder and decoder module. The task of the encoder module, it was to read and process the whole sentence, read and process the entire text or the whole sentence, and then the decoder was to produce produce the translation, produce the translation. So this reads in, processes it, and then passes it on to the decoder, and the decoder then now starts decoding and writing the sentence. RNNs, as I briefly touched on, were one of the most popular architectures to have this encoder decoder architecture and used for translation. So it is a RNN, it is a neural network, a deep neural network, where outputs from previous steps are fed as inputs to the current step, making them more suited for this type of sequential data. We're not going to get into deep details of what an RNN does because there's no the beauty, the advantage is we really do not need to understand what the RNN architecture in order for us to build large language models. But it's just a good stepping stone when we are going to be talking about attention mechanisms. So let's imagine this to be the encoder section of the RNN. Okay, like this, like this, like this, and they are connected. So these are the words that are getting in there, and these are called the hidden states. These are the hidden states. So the hidden states themselves, they are getting it's like this hidden state. It is no, no, no. Like this word. This word here could be do. I think it's do if I pronounce it well. So this do would then get into this hidden state, but this hidden state also carries information from the previous step. Also gets information from the previous step. Same as here when this mirror gets into the model, it's also getting information from previous steps, and so on and so on and so on. So this hidden state at the end here, it gets the current step information, the word that is there currently, and also gets some information from what has happened previously. So this hidden state here should carry all the information of the input sequence, including the current last step. And then that last hidden step is then passed into the decoder section. It's then passed into the decoder. These are the hidden steps, right? Hidden states, right? And then it starts sp- spitting out the translation help, and so on and so on and so on. These are also connected. So as it is feeding, it's also connected. Can you help me on the decoder that I've spit out can, it- and then the hidden states would talk about the next word, space out the next one, and all of that. So what essentially is this memory cell memorizes memorizes the memorizes the entire text and passes it on to onto the decoder. That's pretty much what we wanted to highlight there. We're not going to really, again, we're not going to really get into the actual. Let me see if I can if I find the current neural network. I'll find. Let me quickly grab an image of what a recurrent neural network actually looks like. Yeah, I think this one will work. So this is this. Let me see. I'll paste it now. So this RNN, that recurrent neural network, is just showing that as information is passed from information is passed from one step to another, there are outputs, but at the same time, with that, even though there are outputs here, there is also information that is passed on to the next step to help with the calculation of the next step's output. And then the next steps outputs calculations are passed on to the next one to help with the calculation of the next step output. That's pretty much what it's doing all the way up to the end. So now the encoder is fed input text, which processes it sequentially. And then the key idea here is that the encoder part, it processes that entire text, input text, into a hidden state, the memory cell, as we saw here, as we saw there, this memory cell. And then the decoder takes in its hidden state to produce the output, takes it into its hidden output, hidden state, and then starts producing the output. You can consider this encoder as the embedding vector, like we discussed previously. This can be thought of the embedding vector as we discussed. But the problem with these encoder decoder RNNs is that RNNs, they can't directly access earlier hidden states because everything gets put into this memory cell and that's it. They can't access anything before that. And this decoder here, the only way it can access the text, entire text, is just by interacting with this memory cell. It can't say, "Oh, I'm at this state. I'm now translating this next word. Let me see what has happened before." It can't do that. It can't directly, or this one can't directly access this part here. It can only it can only interact with the history based on what has been passed to it by the previous cell. That's all. So it relies solely on the current hidden state, which encapsulates all relevant information from previous steps. This can lead to a loss of context because if it passes it wrongly, it can't really know what is that on what is being passed to me is wrong. And also memory limitations and all of that. You can only pass so much information. You can't pass the whole text, so some information gets dropped. And by the time you get to the end, it probably is passing information that is not good enough. So that loss of text, especially in long sentences where dependencies might span long distances. Imagine we are talking about London, and then I say London in the beginning, and I have all this stuff where I don't reference London anymore. I'm now just saying the city, the city, the city. I'm talking about London, and then right at the end, I want to describe something in London. It might have completely forgotten that I was talking about London. It just knows that I'm talking about a city. So that is the challenge of this of recurring neural networks, what they faced. So now we are going to get into seeing, okay, now that now that they are now that there's this challenge of long sequences and all of that, and not being able to access earlier states, how do attention mechanisms help with that? So I hope this was good motivation enough for why we moved from recurrent neural networks two transformer models that have an attention mechanism. So let's see the attention mechanism in play in the next video.